All right, we'll go ahead and get started. Again, my name is Andy Bragg, and I'm the Director of Sales with SKC. We have a couple of panelists joining us today. We have Beth Sackett, who is the President of SKC West, who will be with us, and also Salia Strakamus, who is our aerosol physicist and also the Head of Product Development. To get the presentation started today, Dusty Ott, who is the Corporate Industrial Hygienist for SKC, will be getting us started. And Dusty is a CIH, so he's very familiar with a lot of these things in regards to sampling. And he has a history in mining, so he has some real good experience to associate with this as well. So Dusty, if you want to go ahead.
Awesome. Thank you, Andy. Can you hear me?
Yes,
And
very
you can
well.
see my screen, right?
Yes, sir.
Very good. Well, awesome. Well, thank you for everyone who's on the call. We're excited to go through this presentation with you to the best of our knowledge. And knowing that the proposed rules should be coming out anytime, we'll do our very best to answer any of those questions that you have. So with that, here we go. Get over here. Okay, so we're going to start by going over why silica is bad, why we should care about it. We're going to go over the proposed rule. We probably won't read it page by page, but we'll have a fun time going through it. Take some of the highlights out, the things that really matter, and the points that are going to matter to the miners and the operators as well. We're going to briefly go over some size selective sampling, how to correctly sample for silica, and at the end we want to leave some time for any questions and answers that you might have. So I'm going to shoot to get this done in about 45-50 minutes with me and Andy's points, and so we'll have some time at the very end for questions. So with that being said, a brief overview, and this might be common knowledge to some people on the line. Sometimes some people may not completely understand how and why silica is so bad. So we're going to take a second to go over that to make sure we all understand why it's not something that we should be breathing on a daily basis. So it's a sharp little crystal that's going to travel deep down inside of our lungs and to create issues with us being able to breathe down the line. And so to get a picture of what some of these small little particles look like, I've always thought that these things look like little baby arrowheads on filter paper. And so I took some illustrative liberty and made my own little arrowheads on some filter paper. But that's effectively what these little particles of silica are. They're sharp little crystals that stab our lungs, that create a lot of issues for us. And it doesn't take very much to create damage down the road. And so as far as the actual motor damage, like I said, those small particles, we breathe them in, and only the very smallest ones make their way deep down inside of our lungs. The bigger particles, the visible dust that we can see in the air, a lot of that is taken out inside of our nasal passages, our mouths, the back of our larynx and pharynx, and even impact a little bit down here, down into our lungs. So the small particles that we're worried about, and that's what this whole MSHA the proposed rule is about, is the very, very small particles that they're making their way deep down inside of our lungs, down into the alveoli, where they really cause some issues. So this is a really incredible picture. This is a white blood cell, and this is a small piece of respirable crystalline silica. And this white blood cell is about to consume that piece of silica. And what's going to happen is when it consumes that, it's going to move into the actual interstitium of the alveoli. And then at that point, that white blood cell will not be able to digest or get rid of that little piece of silica. And so it will die. It will trigger a response to where other white blood cells come and try to attack it, try to take care of it. And what happens over time is the more pieces of silica you have inside of your lungs, the more and more white blood cells are going to come and try to take care of them. But in the end, they're going to die and eventually cause scarring and fibrosis over the flexible parts of your lungs. A good example that I like to think about is if you have a balloon and you wrap that balloon in tape, you're not going to get nearly or any of the movement that you want compared to when that balloon is new and flexible. And so by keeping those particles out of our lung, that's the way that we're going to be able to make sure our lungs stay flexible and happy throughout our life. And so this is a really awesome picture that the CDC made during COVID. And so I took the liberty of adding our little piece of silica right here on the scale. And so this is a piece of between 4 and 10 microns. As you can see, it is smaller than red blood cells. When you compare it to the size of a white blood cell, it's significantly smaller. I mean, we are approaching the size of bacteria and smoke. Like it is such an incredibly small particle, and that is why it is able to travel deep down inside of our lungs. And so before we get too far into the rule, we talk a lot about this micrograms per cubic meter. What does that mean? Like I said at the beginning of this, for a lot of the verbiage and a lot of the concepts are going to make sense to a lot of us, but if anyone does not understand what this means, what we are doing is we are taking the mass and we are seeing how much mass is in a given volume. So it's a mass per volume concentration. And as we go through this rule, we're gonna learn what MSHA thinks, or what MSHA has stated that the new concentration will be, and it all starts with the microgram per cubic meter. And to help us understand this a little bit more, what is a microgram? A microgram is a millionth of a gram. Like it is such an incredibly small number. It's kind of like when you see pictures of our solar system and you see the little Earth next to the sun. Like it's massive. I know the sun's huge. I know there's other stars that are way, way bigger than us, but it's hard for people to understand the things that are really, really, really big, like stars. And it's also hard to understand things that are very, very, very small, much like silica, like we're talking about today. So this little piece of, little grain of sugar is about the weight of 50 micrograms to give you some scale of what we're talking about. And then going to the next bit, how big is a cubic meter? And for those who don't speak metric, there's the Americanized version of it, but a cubic meter is just what it sounds like. It's a meter by a meter by a meter. And so what we're doing, the relationship that we're making is that we're taking 50 micrograms, so approximately the equivalent of a single grain of sugar, and you're evenly distributing it within that cubic meter of air. And I think it goes without saying, I'm going to go back up to this slide right here, that if you notice right here, the visibility limits of what the naked eye can see are in this area. So anything below this line, we cannot see with our naked eye. And so when we're walking outside, when we're at night, if by chance we're underground at a mine, and your cap lamp shines through a plume of dust, all that visible dust you can see is going to be in this range. It's bigger than 15 microns. And so you can imagine that if we're trying to distribute a single grain of silica in this space, you are not going to be able to see it. So just because you can't see dust in the air does not mean that it is not an issue. This is an awesome illustration. Did a little backwards calculation on the math. Is if you put enough silica to cover up Mr. Abraham Lincoln's forehead, which is 1.4 milligrams, and you evenly distribute that within 28 cubic meters, you're going to be right at that 50 microgram per cubic meter that we talked about earlier. So it's a very, very small amount. It does not take very much to overexpose miners to this new concentration. And it's something that we all should be very aware of and doing our very best to help meet that new rule. And so I've kind of alluded to it, but our new proposed, the MSHA proposed PEL, which is the permissible exposure limit, and the action limit are 50 micrograms per cubic meter and 25 micrograms per cubic meter. The difference is that 50 micrograms is the regulatory limit, and 25 micrograms is the limit at which you start needing to implement some controls to reduce your exposure. But the kicker of all this is only calculated for an 8-hour time-weighted average. And so to kind of preemptively help everyone understand how this calculation works, we're going to do a little bit of math. So don't be too scared. I've made it as easy as I possibly can, but I want to make sure we understand how our results look on a lab sheet and how we can make sure that our results are going to be in accordance with the 8-hour time-weighted average that MSHA is going to be comparing against. So to start things off, we are going to look at a simple sampling report. This might be a sampling report that we got back after we did some sampling at the crusher. We want to know, what our exposure is, if we're going to be over or under the new MSHA PEL. And so to go over some of the high points on this, we're going to have information like the date, the phone, the person's email, all of this, the stuff that is blacked out. The key points that I want to point out is we have an air volume of 1,300 liters. And the way that, and where that came from is we have our sampling pump set at 2 liters a minute, and it ran for 650 minutes. And if you times, 2 times 650, this is where our 1,300 liters come from. So moving on down the page is on the left side in red. This is our sampling results from a mass point of view only. This is how many micrograms of quartz crystalline silica were on my filter paper that I sent to the lab to be analyzed. Once I do the conversion from 50 micrograms into cubic meters, which we'll do on the next slide, this is where this number comes from. And so moving along right here, so we have our 1,300 liters. And just to make sure we understand how we get from liters to cubic meters, one of the very nice things about the metric system is we are converting cubic liters to cubic meters. There's 1,000 liters. So you're taking 1,300, dividing it by 1,000, and it's giving us 1.3 cubic meters. And then what we're doing right here is we're taking our mass that is on our filter, and we're dividing it by our total volume, which is 1.3 cubic meters. And that is getting us the result of the 38.46 micrograms per cubic meter. And so this is where these numbers are coming from. This is what we're going to see on the actual page. So I told you it was going to be kind of interesting. And so this is the example that MSHA gave in the actual rule. The proposed rule is, the example they gave is if you have 55 micrograms of respirable crystalline silica on your filter paper, and you sampled at 1.7 liters a minute, you will end up with a N concentration of 67.4 micrograms per cubic meter. Now, looking at this, for me, it's not the easiest math to do. The 1.7 liters isn't very easy to divide out. And so I made a little bit simpler example on the next page for us to go through. So what the rule shows is what you're doing is you're taking the total weight of your contaminant in micrograms, and that's what you collect over your full shift. Then you're going to divide that by your flow rate times 480 minutes, which is the 8-hour equivalent. And then you're going to times it by 0.001. And what this does is this is converting liters to cubic meters. And so if we do the same math, so right here we have 55, 1.7. Right here for our example, we have 50 micrograms. We sampled at 2 liters a minute for 480 minutes for the 8-hour equivalent. And then what this is going to give us is our end result. It's going to be 52.08 micrograms per cubic meter. Now, as I was doing this example a couple times, I thought it was really interesting that this value, once you times this all out, your value is 0.96, meaning it's almost equivalent to 1. And so if you notice, if we have an example from our lab report of 50 micrograms on the actual sampling report, the end result is almost exactly the same, but in an 8-hour time-weighted average. And so to kind of illustrate that even more, we have on our filter paper from the lab, we have 50 micrograms, we have 25 micrograms. From our lab report, again, 38.46, 19.23, as it stood with the 1,300 liters that we divided out. But because of the 8-hour corrected time-weighted average that MSHA has given us, you'll notice we have 50 micrograms on the paper. Our end result in an 8-hour time-weighted average is almost the same. It's 52.08. Now, if you took this for 40 or 60 or 80, it's going to be within 4% of what your micrograms are to what your corrected time-weighted average is for your MSHA value. I thought that was a really cool, really nice and easy way to understand and look at your sampling results. Like, you can get your sampling results back. You don't really even have to do any math. You kind of do a qualitative look at it. You're like, hey, I got 50 micrograms on my paper. Yep, I'm gonna be at or above the 8-hour time-weighted average. Whereas if this was 25 micrograms, like, yep, I'm definitely under the new PEL of 50 micrograms, but I'm over that the action level of 25 micrograms. So I thought that was kind of a fun qualitative way to be able to look at some of these results that we're getting from the lab and make it a little bit easier to get that conversion. And what's interesting is that conversion works best and only works best with something that's at 2 liters a minute. So if your cyclones are at 1.7 or 2.5 or something other than 2, this calculation is not going to be quite as simple as with something that is 2 liters per minute. But just wanted to throw that out there for you. So with that all said, everything moving forward that we're going to talk about is going to be in reference to the corrected 8-hour time-weighted average that will be calculated from our sheets, from our lab reports. So that being said, we are going to move on to the new MSHA proposed rule. And the main question I have is are you ready? I have a giggle every time I see this, so hope you like it. Okay, so as far as the current timeline, from the best that we understand, is we are expected to see this rule by the end of April. As of today, it is April 10th. So it gives us about 3 weeks. Hopefully we see that before the end or the beginning of May. The final rule is going to take effect 4 months or 120 days after that is published. And then the baseline sampling that each operator needs to take care of needs to be done within 6 months of that date. So if, for example, if today, if MSHA dropped the rule today, in 4 months from today, that rule is going to go into law. And then 6 months from today, we need to have our baseline sampling done and ready for MSHA. So I have a couple asterisks here, and it's kind of interesting. Within the first 180 days, each miner. So this is what has to happen for every single person. So mine operators, they need to get the sampling equipment, or the contractor or whoever might be coming on site to their sampling. They need to understand what occupations or what jobs could potentially be over the PEL, or not even that, but exposed to silica. Make sure you're identifying the correct laboratory, arrange analysis, and right here is determine who is reasonably or expected to be exposed to respirable crystalline silica. And so MSHA says that pretty much anything that has to do with extraction meets that point. And There is mention inside the rule that representative samples may be permitted, but the kicker is the miners have to be doing the same task, the same shift, and in the same work area. I don't know how many of you have worked underground before, but I know the time that I spent underground, one drift could be exposed to, you have like 10% silica in the rock. You go around the corner into the next drift, and it's going to be a completely different silica concentration. And so being able to do representative samples that meet all of these requirements will definitely be challenging. So something to keep in mind as you start planning for your silica sampling in the days to come. So in the rule, it calls out two different types of sampling or analysis. One of them is going to be quantitative and one of them is going to be qualitative. This first one that we have up is the quantitative, and that's to evaluate the actual risk of the employee. That's taking actual air samples in their breathing zone and submitting them to a lab to have somebody give you an actual result, so you know exactly how much is in the air. And then based on this, you can check the efficacy of your engineering and administrative controls, as well as understand where or where not you may or may not be exposed to silica. So the other part of that is a qualitative evaluation. And what's really interesting is this goes into effect 18 months after the final rule drops. But it's interesting as you read through it that if there's any changes in production, process, engineering, personnel, administrative controls, or any other factors, including geological characteristics, you have to resample. And so this is a pretty interesting underground map. These are all drill holes going down, and inside of all these drill holes are the cores that allows geologists to know what is in that rock. This is how they know how to plan mining and where they're gonna go after the gold per se, if that's what they're going for. So in each of these areas is going to be different concentrations of silica, different concentrations of other minerals. And so it's very interesting that they included geological characteristics that you'll have to reconsider every 6 months as you go. I mean, you can go one day to the next and you're going to have different geological characteristics. So hopefully, I'm hoping to get a little more clarification on this part of it once the final rule comes out. As far as our hierarchy of controls, we do not have the luxury to eliminate or substitute the silica out of the rocks in which we mine. And so we are going to be starting here at engineering controls. And what this does is this allows us to have something engineered in place that will help control the dust. This is something like a baghouse or a vacuum system or a fume hood or something like that is in place. Administrative controls are say, hey Joe, you can't go down there, between 5 and 7 because the silica is too high. Well, if he decides to go down there, there's nothing you can really do. There's nothing preventing him from doing that. And that's why engineer controls are better, because administrative and PPE controls, they can be easily defeated based on people's choices. So briefly going over, these are some of the engineering and administrative controls that are in the rule that MSHA calls out, specifically ventilation, dust suppression, and enclosed cabs. A note on the enclosed cabs, I'm sure if anyone has dealt with enclosed cabs, you already understand this, but enclosed cabs only work well if the door seals are in place. A lot of times going sampling on a cab that's enclosed, we can't understand why the exposures were high, but the door seals are completely missing. They're gone. So make sure if you're relying on your enclosed cab that the door seals are part of their pre-work inspection to make sure they're keeping all the dust out. And as far as some of the administrative controls, we have housekeeping, positioning, clean for spills. And what's really interesting under this current proposed rule is that worker rotation is not allowed. Now, I think that this part needs some additional information from MSHA, especially in certain jobs when not every person in the mine is trained at that job. One that would come to mind is is underground. The gentleman that's running the crusher that's putting, as the haul trucks come and dump their load, he's using a rock breaker to break up the rocks to make sure they're going to be able to slide down through the screen. What happens if he's overexposed to silica? I mean, not every single person in the mine is going to be able to come and take over his job and keep the rock moving up the skip. And so hoping that we see some additional clarification on worker rotation and kind of what that is going to mean in the mining world. So as far as that third line of protection, or PPE, this is not an acceptable method of compliance. For example, in this picture, look at this gentleman operating the longwall. He is wearing a respirator. He probably wears that respirator every single shift, all day, every time he's underground. Interesting that he's wearing shorts. But in the proposed rule, this type of PPE for this type of procedure or process would not be allowed. This type of this dust would need to be somehow engineered out of the equation, and you could not rely wholly on PPE to protect you from that hazard. Again, this has been a major point of concern across the board. And again, I'm hoping for more clarification from MSHA on their stance on this once the final rule comes out. These areas down here are areas that they've deemed appropriate to wear respiratory protection. And that is if there's not any engineering controls yet in that area, if they've entered a hazardous atmosphere, or if they're doing non-routine maintenance or investigation. And a really good point that was brought up at one of the last presentations was, is maintenance work considered non-routine? And that's a good question that I hope that MSHA will answer once they give us their rule. So as far as our baseline monitoring, we need to take these within 180 days, within 6 months, once that final rule has been dropped. And so if we take our samples, we get our samples back. If they are below 25 micrograms per cubic meter, then we need to sample again within 3 months. And what that is doing is that's giving us the assurance that, yes, our first samples were below 25. These next ones were proving that our initial samples were correct. The only caveat is just got to make sure that the 2 consecutive samples are at least 7 days apart. And then after that, you can discontinue that part of the sampling. And I put a picture of a control room in this because that's what a lot of these jobs are going to be, that are below that 25 micrograms, or are the people that aren't actively out actually in the mine doing the actual mineral extraction. So this might be a stretch saying that we have to sample control room operators, but these are just people that might not be exposed to as much as others. So moving on down the line, if we are between 25 and 50 micrograms, we have started a process that we call periodic sampling. And what that means is, once we've taken that and gotten that initial sample back, we need to go back and resample every 3 months to see if we are still in that 25 to 50 microgram per cubic meter range. If we're still in that range, then we're going to continue to sample every 3 months until we get samples back that are below 25. And similar to the first set, is if we can get two consecutive samples back in a row, at least 7 days apart, that are below the 25 micrograms, we can discontinue the use, or we can discontinue periodic sampling. So what happens if we're above 50 micrograms per cubic meter? This is when you have to take immediate action at this point. And so it's kind of a cycle, and I know there's a lot of words on this slide. So as we walk through it, here we go. So we are going to sample. This could be our baseline sample. This could be samples that we've taken after the fact. So we sample, we get our results back. We're above 50 micrograms. We are immediately going to put in some form of corrective action. Once that corrective action has been put in place, we need to resample. Once we resample, our results come back. If they're still above 50 micrograms, we need to put in another corrective action. Once that corrective action has been put into place, we need to resample again. Now, this is a cycle that will continue until our results fall less than 50 micrograms, whether that's in between 25 and 50 or below 25. And just like the previous slides before, we have 2 samples below 25 micrograms, at least 7 days apart, to kick us out of periodic. And then once we get into that below 25, 2 more samples within 3 months that are at least 7 days apart, that will help us discontinue the use of that periodic sampling. So as a continuation on from the previous slide, when results are greater than 50 micrograms, there's a number of things that have to go into effect right away. The first one is pretty crazy. Respirators must be made immediately available to the affected miners before the start of the next work shift. So some of the mines that I've worked at, this is not going to be as big of a concern because they're already fit test. They already come to work clean shaven every day. They would simply just need to go grab the respirator and go to work. Whereas other jobs or other mines, they may not have that already in place. And so ask yourself, if I get my results back today, would I be prepared to send our miners back into that area with respiratory protection? That means they have a physical, they have a pulmonary function test, they've been fit tested, they have a respirator, and they have the right cartridges, and they're clean shaven. So just make sure that as you go through the thought process, to make sure that if this happens, that you're ready, that you are ready for it. So, and once you hit 50, you're beginning or you're continuing on that corrective action cycle until you are able to engineer those exposures to below 25. So this is a little MSHA compliance-o-meter that I made to help make things visually maybe a little bit easier to see. So we have our green zone down here that are our results that come back below 25 micrograms per cubic meter. We are good. We are happy. The results that come back between 25 and 50, this yellow zone is our periodic monitoring zone. This is where we will continue to live until we can move our sampling results from this area down below 25. So this red area is the area that is above 50 micrograms per cubic meter. This is where we have to do we have to make changes immediately. People have to be in respirators. We have to continue to resample to make sure that we're doing everything we can. We have corrective actions in place that we're checking continually. We do not want to live in this zone. This is not a happy place to be. Being able to move from the red to the yellow is a better step. And ultimately, obviously, getting down into the green zone is the place that we want to be. And so we briefly talked about respirators before, but it's only considered a temporary solution. You can't use it full time. There would be times that I'd be underground, and for certain jobs, whenever you were in that area, you were wearing a respirator from the second you got there to the second you left. That type of thinking moving forward is not going to be allowed. And so one point of interest is if the miner cannot wear a respirator, you have to move them, you have to accommodate them and move them to a separate part of the mine or to a different job where they're not going to be exposed to silica. So we briefly went over this before, but basically if conditions change, you need to resample. If your haul truck broke down and for a couple days and your roads are all dirty, if the vent bags were moved, were knocked down, if you got a new crusher, if you're in a new ore body, if you have new people, like there's so many different factors that could fit into this paragraph that would cause people to resample, that it definitely would make sense to take some good time, run this through the scenarios based on your own mind and understand what you would need to do to make sure that you can comply with this part of the rule. So as far as actually collecting the samples, we're going to go into more detail on this a little bit later on. But generally, they need to be full shift in the breathing zone. They need to meet the ISO curve. These are the current methods that MSHA recognizes that we can use. And like I said before, you can use representative sampling, but it has to be the same task, same shift, same work area. So night shift, day shift, different sampling. You know, these guys could be working in this drift, whereas you move one drift over, and that wouldn't be considered the same work area. And so just keep that in mind when you're planning out your sampling for the coming months. As far as record keeping goes, there's a lot of data that needs to be collected, not only during the time that you're sampling, but also once those results come in and you make a report to present to people. These are some of this is what is called out specifically in the rule from MSHA. So these are a couple example sheets that I've used in the past. Like the screen says, this is purely an example. You can use something like this. You can make your own. I'm sure there's canned forms that are available, but there's a couple pieces that I really wanted to point out. Calibrator, your serial numbers from your calibrator and your pump, your sampling media, your lot number, expiration date, your actual sample ID, and your pump number. And so these are identifiers that allow you to trace those samples from start to end. If you have everyone wear a sampling pump, you don't write down what pump number they're using. You don't have records of the cassette number. Once you get those results back, it's impossible to correlate how much volume went through each pump, and therefore you wouldn't know which cassette belongs to which people. So as with most things with MSHA, record keeping is an absolute must. And so this next picture, I have kind of outlined where what you'd be looking for. So this is our flow meter serial number. This is the number on a PPI, serial number over here on a pump, and this is where the expiration date and the lot number could be found on one of our PPIs. Depending on the pump you use and the media that you use, it may or may not be on the same area, but just they'll be there. So this one is the medical surveillance section. This deserves its own webinar. Like, there is so much stuff that's packed into the medical surveillance part of this that I'm going to highly encourage you to go through that section in the new proposed rule. It's 60.15, and to be able to make sure that if you are currently doing physicals, that they are meeting up with what MSHA is proposing here. But definitely take this one offline and spend some time going through the medical surveillance section. So quickly, we're gonna go into the air monitoring part of this. And to start things off, what is industrial hygiene? I asked Google what industrial hygiene was, and this is the picture that came up. Now, if I had to guess, this is one of those amazing AI generated pictures, because it looks like somebody in an industrial area cleaning things up. That is not what industrial hygiene is. What most people think this is in the public. My last plane trip, I sat next to a lady who asked what I did. I told her I was an industrial hygienist, and like countless times before, she says, "Oh, so you clean teeth?" No, I do not clean teeth. And then what industrial hygiene actually is you're kind of like a Superman. And yes, that's me. Before I came to SKC, I was a stunt double for Henry Cavill for Man of Steel. So in all jokes aside, being an industrial hygienist, taking these samples is a way that you can be your own little Superman. You're able to help people, you're able to better their life, and you're able to take that information and you're able to help put controls in place that will not only reduce their exposure, but also increase their quality of life. So I always like to think of myself as a little bit of a Superman whenever I'm doing my industrial hygiene work. So size selective sampling, why is this important? So if you remember from the picture we showed earlier of the different scale of the particles that are small enough to make their way deep down inside your lungs or what are called respirable particles. They are between 1 and 10 microns. And so size selective sampling specifically captures those size of particles and gets rid of the ones that are bigger. And so we're going to briefly talk about cyclones or PPIs. And what these do is they filter out the large, not filter out, they get rid of the larger ones and keep the smaller ones. And so how does it work? Is in a cyclone, the air comes in because of the mass of the larger particles, they are getting spun in a cyclone, and those big particles are being dropped out into what's called the grit pot. And then those smaller particles are making their way up, and those are the particles that are being collected on the media. As far as the PPI goes, it uses something similar to what our own body does. As we breathe air in, or as air comes through the PPI, if it's large, it's going to impact on these pre-oiled impactors. If it's small enough, it's going to make its way past the impactor and make its way into the actual body of the cassette, and where it will be collected on the filter paper. The way that I like to think of it, the way that makes sense to me, is that respiratory particles are like a little ninja. They're very agile, they're very small, they're fast, and they do a lot of damage. Whereas you compare that to inhalable particles, they are large, much like the Hulk. He cannot take a corner. Like you watch him in any movie, as he's running, as he tries to take a turn, he ends up crashing into the building and causing all sorts of havoc. Whereas our nice little ninja, he can make those corners super easy and make its way deep down inside of our lungs and create some havoc. So some of the shortcomings to be aware of cyclones, I'm not going to read through all of these. Just understand that there are definitely some maintenance needs that has to happen with these. You can't have these things tilted on their side or tilt them upside down. If you tilt them upside down, all those particles that have collected in the grit pot will make their way up on the actual filter paper. That would skew your samples and make that not valid. Moving on, these are some of the different cyclones available through SKC. This is the ISO curve, and as you see, each of the cut points is at 4 microns, so it follows that curve fairly well. Moving on to some of the benefits of the PPI. There's a simple calibration adapter that clips right on the top. Because these parts are disposable, you don't have to take them apart and clean them between samples. There's different flow rates depending on the amount of silica in the air. You can run these things just like they're sitting, upside down, backwards, not backwards, but in the orientation, and you're allowed, and then the sampling results will not be skewed because there is no grit pot that is going inside of these. There's the little piece of oiled impactor that's collecting those larger particles. And this bad boy very closely follows that curve, as you can see right here. So the dotted line is the ISO curve, and these are the 3 different flow rates that are following that curve. So if you use the wrong flow rate, your results are, like he says, they're totally useless. And so the reason for that being is if you use a higher or lower flow rate, you are going to collect larger or smaller particles depending on what the new cut point is. So make sure before you sample, and Andy will talk about this in a second, that make sure that your flow rate is exactly the same as what it is required by the manufacturer of your cyclone or of the PPI. So with that being said, Andy, it's all you, buddy.
All right, good job. Thank you very much, Dusty. If you have any questions on what Dusty has already covered, now would be a good time to go ahead and enter them in the chat, and we will address them shortly as soon as I'm done with this section. So Dusty has already done all the heavy lifting to this point. What I hope to accomplish in this short 10 minutes of the presentation is to convince you of 2 things. Number one, if you do in fact need to perform personal air sampling as part of the new rule and you haven't done it before, you do not need to be intimidated or stressed out by this process. I assure you it is much easier than you might think. And it's, just all new technology and user interface is so much easier today. This is not something you should stress about. I realize it adds to the workload. Of course, I can't help that. And there's a lot of difficult things and calculations that Dusty has talked about, but this part should be very simple for you. The second thing I want to convince you is that if you have any issues, you have any questions, just call the SKC team and we'll be happy to help you answer any of those questions and guide you a little bit. There's no need to spend a lot of time trying to figure it out. Between our corporate CIH that you just met and our sales team worldwide and our tech services team, we'll be able to help you and do whatever we can to get you going. So in respect of time, to jump right into this, I want to talk about basics of the air sampling. So basically speaking, you need to start the process of preparing to do air sampling by, number one, selecting the proper air sampling pump, which we will talk about all of these individually. Select the proper sampling device or media. And when I say sampling device and media, that's what will actually collect the silica that you will then capture and send to a lab for analysis. Then select the proper flow meter. Now, some of you may know this as a calibrator because that's what we've always called it in the past, but recently there's been a change, and I'll talk a little bit more about that. We're moving away from the term calibrator, and we'll use working standard or flow meter. You need to perform a flow verification. You need to then put the device on the subject or the employee and collect the sample, and then perform a post-sample verification, or again, to use the term calibration. And then lastly, document the sampling details before sending them to the lab. Next slide, please, Dusty. So when you talk about pumps, you may think, well, I just need a pump. Well, there's a lot of different pumps out there. There are pumps that we refer to as low flow that might be for gases and vapors at a very low flow, then medium, or what some people may call high flow, which is going to be in the wheelhouse for what you're doing. And then there is, excuse me, then there is high flow or volume sampling pumps that are used for collecting area samples. So what we're going to be looking at is pumps that sample roughly between 1 and 5 liters per minute. That's the pumps that you're going to be looking for. Next slide. So SKC has 3 medium flow range pumps that will all 3 work for you. At this point, it becomes a matter of preference. So I don't want to spend a lot of time on this right now because I want to focus on the process of sampling and not necessarily the process of selling. But just keep in mind that there are choices, and it really comes down to your preference, whether you want a very basic pump or whether you want a pump that has the ability to do data logging and set programming. So there are capabilities for you and features that you can choose based on your application and how often you are going to use them. Next. So now you've chosen the pump that is the proper pump. Now you need to choose the correct sampling device and the media. Here's a couple of samples that you may have seen before and maybe some that you haven't. Dusty already discussed these devices with some detail. So I just want to reiterate that each of these devices are used in conjunction with a pump to pull a sample through a filter. And then that filter will be then sent to a lab for analysis. But you must be sure that device meets the requirements of the MSHA rule or OSHA guidelines if you're on here, not as part of MSHA. We have 3 different types of cyclones shown here, and then we have the PPI. If you've ever used a cyclone, to touch on what Dusty was talking about, and dealt with the cleaning, the setting it up, and making sure that it stays vertical during the sampling process, and then removing it from the employee, you know some of those difficulties that Dusty spoke of. And I'm not bashing these products. We manufacture 2 of the products that you see there as cyclones. We're just kind of stating some of the obvious. But the PPI addresses all of these issues and makes sampling a little bit more practical and efficient. And most importantly, these all have to be at a particular flow rate. And as Dusty noted, if you sample at the wrong flow rate for any given period of time, you can't go back and cross-correlate it after the fact. Your sample, whether it be for 8 hours, 10 hours, 12 hours, your sample is going to most likely be thrown out because you've sampled at the wrong flow rate. So it's very important, even though it's not marked on some of these cyclones, it's important that you do your research and make sure that the flow rate is correct. One of the other advantages to the PPIs, as you see right there on the front, it's noted on each PPI which flow rate. So once you determine based on your application and your environment which flow rate you need to sample at, then you can choose the proper PPI and make sure that that's what you set the pump for. All right, next slide. Now you need to select what we're calling now a working standard, again, formerly known as a calibrator. It's now kind of a working standard is what they call it. as some of you may have called it in the past also. The industry has moved away from that based on a new ASTM standard that was released in mid-2023. The SKC checkmate that you see on the screen is a NIST traceable working standard. Probably what you will hear this called is a digital flow meter or flow meter. The industry is still transitioning and figuring out what makes sense, but flow meter or working standard is what's most common. It meets all the requirements for air sampling regarding to NIST certification, to the accuracy requirements, and of course the performance. As with a pump, you will be using the medium flow range. This checkmate is offered in 3 different flow ranges: low, medium, and high, and you will be looking at the medium flow range. Next. So now you have your pump, you have your sampling device or media, and you have your NIST traceable flow meter, and you're ready to sample. But first things first, you need to set up the sampling train. When I say sampling train, it's exactly what I just mentioned. As you see in the picture on the slide, the sampling train is the pump, the tubing, and then the sampler, in this case a PPI. You set all that up exactly the way you would, and keep in mind that always, 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 before performing your flow verification, you need to let the pump run for at least 5 minutes to stabilize and equilibrate to the environment that it's in. So always keep that in mind. That's something that's forgotten a lot of times, and you may encounter a little bit of inconsistencies at the beginning of the sample if you don't do that. So always let it run for 5 minutes to stabilize. Next slide. So now, before you can actually put it on the employee, you need to verify the flow rate of the pump using a flow meter. And again, in this case, we've taken the sampling train, we've connected the calibration adapter that basically takes us from the sampling media to the tubing so that we can connect to the NIST traceable flow meter. Now you verify the flow. So let's say you've chosen 2 liters per minute and a 2 liter per minute PPI. What you're looking for on the display is 2 liters per minute. If it is not, it's not on 2 liters, you can adjust the pump to increase the flow rate until the flow meter says 2 liters per minute. And on some pumps, you can actually adjust the display to match the flow meter exactly. Other pumps, basic pumps, you're not able to adjust the display, but you can still adjust the flow to perfectly match what you're looking for. Now, again, keep in mind that when you're doing this, sometimes it may require the adapter that I talked about to be able to go from there to the flow meter. So you now set the flow rate to the desired flow, check the reading on the flow meter, and adjust the pump if you're capable to match the flow meter. Now, to collect the sample, you've already got the sampling train there. All you need to do is remove the calibration adapter and flow meter, and then collect your sample for the designated period of time. And then you are required to perform a post-flow verification. So you're going to hook all this back up and perform a post-flow verification. All right, next slide. Once you have finished with your sampling and you have taken your post-sampling flow verification, you then take off the sampling media, in this case the PPI with the internal filter. You put the little black cap that you see in the picture, and you actually would have a sticker provided that you put over these 4 holes because you don't want it to be exposed to anything else once the sampling is complete. You make all the documentation and pertinent information that the lab needs to perform the analysis, and then you package it and ship it to the lab for analysis. And that, pretty simply put, is all you need to do for the air sampling. The one little piece of the puzzle, and I'm going to talk about this again in a minute, when you're sampling and you're doing your pre-sample flow verification, you're going to want to use a surrogate device exactly like the one you're going to be doing sampling with, and that's what you're going to do your flow setting and everything with, so you're not exposing it. So in the illustration that we have here, this PPI that you see in the picture would be basically a surrogate. You would perform the whole flow verification, make sure the flow is set exactly where you need it, and then you would take that device off, put the actual sampling PPI that you're going to use before putting on the subject. And that just makes sure that all the exposure that you're recording in the sampling device was recorded in the area where you were doing sampling. All right, next slide. For some of you, you may have not done this sampling before. You're not sure exactly how much you're going to have to do sampling, and maybe not have the budget for it yet because all of this is new. So what SKC and SKC West has done is prepared a rental kit that you can rent that has everything in it that you will need. You'll have the Air Check Touch in this case, which is the pump that you see there with the color display. You have the flow meter with the proper adapter, and then you have a charging cradle, which is for the pump. And of course, you need tubing to connect the pump to the sampling device and media. And then you have the surrogate PPI that I mentioned earlier that you can use for your flow setting. This gives you the ability to have everything that you need all in one place to do your sampling. The only piece that you would need in addition to this is the number of samplers that you would need. So again, to use the PPI in this illustration, if you're going to be conducting 10 samples, then you'll need to purchase 10 PPIs in addition to what's in this rental kit. But I think it's a great way, an easy way to give you all the information all at once instead of worrying, do I need to buy this? Do I need to buy that? This gives you all of the equipment, and of course, we'll support any questions that you have. Sorry to speak so quickly, but we've only got a couple minutes, and just in case we had questions, I wanted to make sure that we had a minute to address them. So
thank you guys very much. Both of you did a great job. Appreciate it. And we do have some questions. The first one is, does the baseline sampling need to be done in the worst case scenario, the hottest, driest time of the year?
It doesn't specifically say that in the rule. A baseline sampling is something that you're getting your baseline with. And if you're sampling tomorrow, you can't necessarily simulate the worst, driest in July. And so your baseline samples are a place for you to start, not necessarily for you to find out what your possible worst case scenario would be.
Okay, thank you. When respirators become required under the new MSHA rule, what is the minimum level respirator that must be used? Are N95s okay?
I am not sure, Beth. I'd have to go back and find that out and get back to you.
Okay. All right, thank you. Where exactly does it state that respirators are not not a permanent solution?
I would have to get them a page number,
Okay.
but happy to do that.
Okay. Do we have to prove that the flow meter on the checkmate shows the proper values? And if so, how do we do so?
So when they say prove it, what do they mean by that?
And Dusty, I may be able to add a little bit of that. If they're saying prove in that it's accurate, that's part of the whole NIST traceability aspect of it.
Right.
Whether it's the checkmate or a NIST traceable flow meter, it has to go back annually to be certified and that it meets the requirements. So therefore, that kind of is your proof, and that's your documentation that it is reading properly. I hope that is what they're asking. But that is your basis and your backup, that the meter is reading properly, and therefore you're able to set the flow of your pump to that.
Great. If that doesn't answer your question, go ahead and you can put another question in, and we can be sure to answer that afterwards. One of the other questions that we had, a lot of people are asking for the shared slides, and we'll be able to provide that to you. You'll also get a link after the presentation's over to view the presentation all over again for those people that didn't get to see it. One other question that I have, Dusty, this is particularly for you. Is Dusty really his name? If so, what is his personal concentration of RCS?
Yes, my real name is Dusty. So my parents must have knew must have known that this was my career. So
And then it looks like the last question that we have is, do you suspect the PPI to be allowed as media?
yes, I do. Let me get back over real quick. In the rule itself, it specifically calls out that it must follow the ISO 7708 curve. And they did not give us any specifics of what, like, other than it has to meet that curve. The PPI does meet that curve. And so I don't see any reason why they would not allow that to be used.
Great. That's all the questions that we have. So thank you everyone for attending. We really appreciate it. And thank you, Dusty and Andy. You guys did a great job.
Thank you all very much.